Okay, so in our previous video we introduced the idea of the derivative as the gradient function. So creating a rule that describes the gradient of a curve at any point along that curve. And we did that using a process called differentiation by first principles. And fundamentally that's what we're doing every time we differentiate. However, when we differentiate power functions or polynomial functions like we will be doing in year 11. Next year we'll introduce the derivative of all our other kinds of functions, logs, exponentials, trig functions, but for this year we just focus on polynomial functions, but technically power functions, so we could also have negative powers and fractional powers, so hyperbolas and truncuses and square roots, etc. So we looked at how to do that by derivative by first principles. We can, however, establish a rule that will let us do it more quickly than that. So we want to establish that today from the place that we worked from last lesson. So differentiation by first principles. So in the previous video, we manually did differentiation by first principles for x squared, and we found that it was 2x. So I've already filled that in my table here. Okay. So we're just looking at differentiating things of the form x to the power of n. And we did when n equals 2. Okay, we did that last lesson by first principles. Okay, let's calculate these other derivatives. Let's get our CAS to help us do the derivative by first principles. Okay, so let's start off. We'll be able to do this quite quickly once we've done the first one. So let's start off with defining f of x as being the first function in the table, which is x equals 1. No, sorry, not x equals 1, y equals 1, so f of x equals 1. And then we want to evaluate the derivative, which is to calculate a limit. So template palette, limit, as h approaches 0 of f of x plus h minus f of x all over h. So we know that's how we calculate our derivative by first principles. So in this particular instance, when I press enter here, it will do that process for the very simple function f of x equals 1. And when we do that, we'll get 0. And we could do that one by hand. I want you to also keep track of what we're actually calculating here. Remember, we're calculating a gradient function. So if you think about what this function looks like, f of x equals 1 is a horizontal line, y equals 1. Okay? And so therefore the gradient of that curve, not even a curve, the gradient of that line everywhere is always 0. So it makes complete sense that our derivative is 0. Okay? Alright, the next one, f of x equals x. Now again, if you think about what we're calculating as the gradient function, you should be able to work this one out yourself. So if I redefine my function as f of x equals x, and now I calculate the derivative by first principles again for the newly defined f of x, I find that it's 1. f dash x equals 1. The gradient function is 1. And again, if we think about what's happening here, f of x equals x, well, y equals x, that's a straight line with a gradient of 1. Everywhere, gradient is always 1. So it makes sense the derivative function is 1. For every value of x, the gradient will always equal 1. Okay, so then we've got our next one that we did already by hand ourselves. We can confirm that here fairly efficiently. So if we redefine our function as x squared, we calculate the derivative by first principles, we find indeed that it's 2x. Okay, so then let's continue on beyond there. So if my original function was x cubed, I calculate my derivative by first principles, and we find that the derivative would be 3x squared. Alright, so then we redefine our function as x to the power of 4. Derivative by first principles is 4x cubed. So you might be starting to see a pattern. Think about whether you can predict what the next one's going to be. So if we redefine f of x as x to the power of 5, redefine f of x as x to the power of 5, press enter first, and then recalculate our derivative by first principles, 5x to the power of 4. Okay, so the next row in the table makes a jump. If n were to equal 10, so x to the power of 10, again, write down what you think it's going to be. So if the power is 10, the derivative by first principles, as evaluated by my CAS, is 10x to the power of 9. Next one again, we've got this time n is 28. So if you have x to the power of 28, think about what do you think the derivative is going to be based on the patterns that you're seeing. It is 28x to the power of 27. Okay, so I hope by now that you've all been able to see the pattern. So essentially the process that happens to get from the original function to the derivative function, when our function is of this form, x to the power of n, we bring the power down to the front, so it becomes 3 times, and then we reduce the power by 1. So if we were to generalize that, if we had f of x was x to the power of n, then f dash x would be, now we bring the n down to the front, so n times x to the power of, and then we subtract 1 from the power, so it'd be n minus 1. So when we're differentiating things of the form x to the power of n, we get this general rule for differentiating. Again, this is what's happening every time, but what we're observing here is that when we do that, there's a pattern that we can follow that's going to allow us to evaluate the derivative more efficiently than having to do that lengthy process involving limits. That isn't to say that you don't need to know and understand what's happening here with this derivative by first principles. It's a fundamental part of what's happening in the calculus, and you do need to be able to know that. You can expect to be assessed on that. Okay, let's talk then about some properties of derivatives. So if we have y equals k times f of x, okay, so we've got a number times a function, so 2 times x cubed, 3 times x to the power of 5, as I've got in this example here. So we've just got a number times x to the power of n, for example. When we differentiate that, the number doesn't actually have any effect on how we differentiate it. So we're essentially just calculating the derivative of the f of x part, and the number still sits out the front. So for example, if my function is 3 times 5 to the power of x, the 3 essentially sits out there on its own, while we then worry about differentiating the 5 to the power of x. Derivative of 5 to the power of x becomes 5x to the power of 4, and then we just multiply that answer by 3. So 15x to the power of 4. Now I would do that all at once, but it's really important that you understand that the constant value is not actually affecting the derivative. Okay, it's just sitting there, and you're essentially, if you've got 3 times a function, the derivative of that is 3 times the derivative of the function. Okay, so in practice, I wouldn't write out these separate steps, and I'm not suggesting you do. It's just important that we have an understanding of what's happening. So here we would bring the 5 down to the front, which means it's 3 times 5, straight away getting 15, and then subtract 1 from the power. Another key property when we're differentiating is that if we have a sum or difference of 2 functions, so that might be something as simple as this: x to the power of 4 plus x to the power of 3. Okay, a quartic plus a cubic. Okay, the whole thing's a quartic, but in terms of thinking about each term as something of this form, which we know how to differentiate, if we've got different terms of that form added and subtracted to each other, we can then differentiate that just by differentiating each part separately. So if you've got y equals f of x plus g of x, the derivative of that is just the derivative of f plus the derivative of g. You just differentiate each bit separately. Okay. So for example here in this function, we differentiate x to the power of 4, and separate to that we differentiate x cubed, and we're still just adding them together. Okay. That's important because we can do that when it's addition and subtraction. Okay, and so if it's not just addition and subtraction, you first need to simplify your expression. And that's because if we have 2 functions that multiply together, so let's say we had x cubed times x to the power of 5, the derivative of that is not the derivative of x cubed, plus the derivative of x to the power times the derivative of x to the power of 5. Okay. It's really important that you understand that. And in fact, we can actually see that in this particular example. Here, we know that x cubed times x to the power of 5 is actually x to the power of 8. And so the derivative of that would be 8x to the power of 7. However, if we differentiated each part separately, this would give us 3x squared, and this would give us 5x to the 4, and that would be 15x to the power of 6. These aren't the same thing. Okay, this is what we would need to do. So you need to, if you can multiply the things together, obviously you do that and then you differentiate, no problem. But the point is that if you've got 2 things multiplying together, it's not just the derivative of each of those 2 things then multiplied together. This becomes less important this year. So next year we learn something called the product rule. which is a way that we can differentiate when we've got a product of two functions, okay? We don't learn that this year, and that's mostly because we're not differentiating functions that we need the product rule for. So as I said, for example, if your function was x cubed times x to the power of 5, you'd just multiply them together and then differentiate. If your function was x squared times x squared minus 7, you would expand out the brackets and then differentiate. Okay, so you can't differentiate while there's multiplication. You expand it out so that you've then only got, you've then only got addition and subtraction. Then you can differentiate each part separately. Next year, when we add in all our other functions, we might be trying to differentiate something like this. And in that case, you can't just expand out to get rid of the multiplication. So we have to have a way to do that. So we'll introduce the product next year when it becomes more necessary with the other functions. Similarly, we can't differentiate when we are dividing two functions. Okay. So for example, if you had, again, let's take something like if we were differentiating x to the power of 5 divided by x cubed. Okay, it doesn't equal the derivative of x to the power of 5 divided by the derivative of x cubed. Okay, and again, we can verify that here. We would simplify this first. Derivative of x to the 5 over x cubed, x to the 5 over x cubed is x squared, and so that's going to be 2x. If we were to differentiate these two things separately, that would be 5x to the 4 on 3x squared, which would be 5/3 x squared. Again, not the same thing. So it's really important that we understand that if we have multiplication or division, we must first expand brackets or simplify the fraction so that we don't have any multiplication and division. As I said, next year again we'll learn about a product and quotient rule because it will be more necessary next year, for example, if we're trying to differentiate x divided by sine of x. There's nothing we can do to simplify that. We would need to have a way to be able to differentiate that, and that would be the quotient rule, but we'll introduce those next year when they become necessary. Okay, so addition and subtraction, you simply just differentiate each part. Multiplication and division, you need to simplify first so that you only have addition and subtraction of terms, and then you just differentiate each part. Okay, let's just recap some notation. It's really important. I really want you to make getting your notation right a focus as you work through these exercises. Okay, so we sort of have three different notations, and you can't just pick the one that you like and then just go with that forever. Okay, the first one is called Leibniz notation. Okay, and that's where we write a fraction, d something over d something. Okay, now this actually comes from what we're calculating here is essentially a rate of change. Okay, it's gradient basically. Okay, so it's rise over run. It's how does y change compared to x. So we would talk about the run as being delta x, change in x, and the rise would be delta y, change in y. Change in y. And if we didn't use capital delta, if we use lowercase delta, it would be this. And so the gradient is the change in y over the change in x, which has gradually evolved to be dy dx. Change in y over change in x. Now, if our axes weren't about y and x, if they were about a and r, it wouldn't be a change in y over a change in x, it would be a change in a over a change in r. If our axes were about, t and x, if they were about x and t, it would be a change in x over a change in t. Okay, so if we've got y equals something involving x, that's a y-axis and an x-axis, it's a change in y over a change in x, dy dx. The derivative of y with respect to x is how we would read that. If your function is y equals a squared minus 5a, okay, that's y compared to a, the gradient would be change in y over change in a, so dy dA. Derivative of y with respect to a. If your function is x in terms of t, that would be x compared to t, your derivative, your gradient, would be change in x over change in t, dx dt. Okay, so we can use Leibniz notation. Now, if your equation's not given in function notation, you'll have to use that. Okay, if it's y equals x squared minus 3x, the derivative of that isn't f dash x. Okay, there's no f of x in that. The derivative is dy dx. Okay, so it's really important that you work to use notation that's consistent with the question that you're being asked. The second option is the easier one we've been using a little bit more so far, is function notation. So if you've got your derivative as a function, f of x, the derivative of that would be f dash x. G of t, the derivative of that would be g dash t. Okay, so this is derivative of f with respect to t, or sorry, with respect to x. And then the third kind is operator notation, and I've also used that a bit. And that's where you don't have it's not a function, it's not an equation. You just have an expression. You want to calculate the derivative of this expression. Okay, so we want to differentiate this with respect to x. And essentially what this is, it's a slightly neater way of saying, let's say we have y equals x squared minus 5x. We know the derivative of that would be dy dx. Okay, but if we think about, all right, well we can put that in place. That's what y is. So it's actually derivative of that with respect to x. Now we can write it that way, but commonly just we tend to write that bit as a fraction out the front, d dx of x squared minus 5x. So we differentiate this with respect to x. Okay. Similarly, if you had an expression that was involving t, you wouldn't be differentiating it with respect to t. You would be with respect to x, you'd be differentiating it with respect to t. And again, it's the same idea, okay? If y were to be equal to t squared minus 5t, the derivative of that would be dy dt. But if we don't have y, that's okay. It's just, we can just write it straight away as the derivative of t squared minus 5t all over dt, okay, with respect to t. And again, we can then take out that fraction and instead write it this way. Okay, so it's simply just a way of writing the derivative of something without needing to introduce y or f of x, without needing to make an equation. As I said, please make sure that your notation is consistent with the question. Okay, if it's not f of x, then its derivative isn't f dash x. Okay, if it is, v in terms of r, your derivative is not dy dx, it's dv dr. Okay, so and also if it's just given as v equals in terms of r, let's say it's, I don't know, I'm making something up. Won't be, anyway, doesn't make any sense, but let's go say we've got something like that. Then the derivative would be dv dr equals 4 pi r cubed in that case. Okay, you could, this is v in terms of r, it is v of r, so it is technically v dash r. Okay, but if it's not given to you in function notation, I would tend to use this instead. Okay. The other thing to note is it is possible, and you will see sometimes, if you want to differentiate that, sometimes people just write y dash equals 2x minus 5 as the derivative of y, and that's okay, but generally speaking, if it's not function notation, we tend to use the dash with function notation, and otherwise it is dy dx. Okay, so please make your notation a focus. Alright, so let's work through finding some derivatives using our rule, using our properties of derivatives, and making sure that we get our notation correct. Okay, find the derivative of f of x equals x to the power of 7 minus 4x cubed plus 6. Okay, so first thing, what are we going to call the derivative? The original function is f of x, so we can use f dash x as the derivative here. We've only got addition and subtraction here, so we can just differentiate each part of the function separately. We're essentially doing 3 separate derivatives all at once. Okay, x to the power of 7, we differentiate that. It's going to become 7 times x to the power of 6. Okay, then we're going to have minus. Now remember, the 4 doesn't change what's happening here. It's going to be 4 times 3x squared, but I wouldn't bother to write that out separately. I would just do 3 times 4, which is 12x squared. And then the final one, plus 6. Okay, we haven't really talked about this, but this still does fit the rule in that we know that x to the n becomes nx to the n minus 1. Okay, we treat a constant value. We also saw that 1, the derivative of 1 was 0. Okay, and again, that's thinking about what we're finding is gradient function. We talked about, that would be y equals 1. Its gradient is always 0. Again, if we think about this just as an isolated function, okay, well that's just y equals 6, and its gradient will always be 0, so this will be 0. We can also think about it as fitting this rule though, because it can be 6x to the power of 0. because x to the power of 0 is 1. And so that's going to become 6 times 0x to the power of negative 1. And that's just 0, which means the whole thing is just 0. Okay, so derivative of a constant is always going to be 0. So plus 0. So we wouldn't bother to write it. Okay, so there's our derivative. Okay, example 2. Find the gradient of the curve determined by the rule f of x equals 5x squared plus 6x at the point 1, 11. Okay, so we want to find our gradient function and then work out the gradient at a particular point. Okay, so let's worry about that bit later on. Let's first of all find our derivative. So our original function is again called f of x, so our derivative will be f dash x. Okay, so again, we're just adding and subtracting functions, so we just differentiate each bit separately. 5x squared, the derivative of that will be, we multiply by 2, so it becomes 10x, and we subtract 1 from the power, so it'll be 10x to the power of 1, which is just 10x. Now 6x, now remember this is x to the power of 1, so 6x to the power of 1, we multiply by 1, we're going to get 6, and then subtract 1 from the power, so it'll be 6x to the power of 0, and remember x to the power of 0 is just 1, and so we just get 6. So our derivative is 10x plus 6. We now want to know the derivative at the point 1, 11. Now remember this is x equals 1 when y equals 11, okay, or f of 1 equals 11. Okay, so there's no y in this equation. This equation we have here, this one, connects gradient and x. That's the two variables there. So we want to use the x value. The y value is useless to us here. So we want to put the x value into the derivative. So if we're working out the gradient when x equals 1, that's f dash at 1, derivative function at 1. So it's 10 times 1 plus 6. So it's going to have a gradient of 16 at that point. Okay, example 3. Find the derivative of x equals t times 5 minus 3t. Okay, now at the moment we can't actually calculate the derivative of this because we have a product of two functions. So we have to expand it first. So x is going to be equal to 5t minus 3t squared. So get it to a form that you can differentiate. Now we're ready to differentiate. What are we going to call the derivative? Okay, we are differentiating x with respect to t. This is dx dt. Change in x over change in t. Derivative of 5t, remember that's 5t to the 1, will just be 5 because it will become 5t to the 0. So it's just 5. And then we're going to have minus 2 times 3, which is 6t to the power of 1. So 5 minus 6t. Please be careful about your notation. This line here doesn't equal dx dt. Make sure you introduce the derivative notation at the point where you actually calculate the derivative. Seems obvious, but the number of times I see the dx dt written next to a line that's actually equal to the original function, not the derivative function. Okay, example 4. Find the derivative, with respect to x of 2x cubed plus x. Okay, so this is just operator notation, so it's not going to be equal to anything else. We are finding the derivative of that, and straight away we can say the derivative of that is equal to 6x squared plus 1. Remembering again this is x to the 1, so it becomes 1 times x to the power of 0, which is just going to be 1. Find the derivative of y equals 6x to the 6 plus 3x cubed over 2x squared. Okay, so we've got a quotient, which is a problem, so we need to simplify it before we can differentiate it. So it still equals y. I'm going to split that into two separate fractions. This is the same as 6x to the 6 on 2x squared plus 3x cubed on 2x squared. So again, I haven't differentiated, I'm still just simplifying the original expression. 6 on 2, that's 3x to the 4 plus 3 on 2 x to the 1. So that's my function. There's no differentiation happened there, that's just simplifying the function. Now we're going to differentiate, so what will we call the derivative? In this case it is dy dx. And then we can differentiate. So we're going to do 4 times 3, which is 12, x to the power of, we subtract 1 from 4, so we get 3. And then remember this is x to the power of 1, so we're going to get 1 times 3 on 2, plus times x to the power of 0, x to the power of 0 is just 1. Alright, example 6. If f of x is x plus 2 times x minus 4, find the y-coordinate of the point where x equals 3, and find the gradient of the tangent line at that point. Okay, so we want to do a couple of things here. What is y when x is 3? So we're going to substitute that into our formula that connects y and x, okay? F of x being the y coordinate, okay? So f of 3 equals 3 plus 2 times 3 minus 4, which means we get 6 times negative 1, so negative 6. So therefore, we go through the point 3, negative 6. So the y coordinate is negative 6. So that's the first part of the question. Then find the gradient of the tangent. Sorry. So remember, the gradient of the tangent, sorry, my pen stopped working for a minute. Find the gradient of the tangent. So remember, the gradient of the tangent is equal to the gradient of the curve at the point. Okay, so we essentially want to find the gradient of the curve when x equals 3. So therefore we need the derivative function. But before we can differentiate this, we've got a product of two things, so we want to simplify that first. So f of x is x plus 2 times x minus 4. If we expand that out, that's x squared minus 2x minus 8. Now it's in a form that we can differentiate because we've only got addition and subtraction between the terms. So f dash x is 2x minus 2. And now we want to find what is the gradient when x equals 3. Okay, so we want to know f dash at 3. So that's 2 times 3 minus 2, which is going to be 4. Okay, so therefore the gradient of the tangent at x equals 3 is 4. And that's the same, that's equal to the gradient of the curve at x equals 3. Alright, example 7, must be getting near the end I think. Yep, this is the last one. Find the coordinates of the point or points on the curve f of x equals x squared minus 3x plus 1 where the gradient is 0. Okay, gradient is 0. So that means we want to work out where the derivative is equal to 0. Okay, so let's first work out the derivative. F dash x, in this case, is 2x minus 3. Now we don't want to sub 0 in here. That would be working out what is the gradient when x equals 0. That's not what the question's asking us. We want to know where is the gradient equal to 0. Okay, so we want to know where does that equal to 0. So that will be when 2x equals 3. So when x equals 3 on 2. Now we want the coordinates of the points. So this is the x coordinate of the point. So what we've got here is a parabola. We're finding the gradient is 0. Now thinking about a parabola, we're going to have 0 gradient at the turning point. This is the way we can find the turning point. We find the gradient is 0 when x equals 3 on 2. And so therefore we want the y coordinate. So we're going to need to substitute that not back into the derivative. We already know when x equals 3 on 2 the derivative is 0. We want to substitute that back into the function to find the y coordinate. So f of 3 on 2 is 3 on 2 squared minus 3 times 3 on 2 plus 1. So that's 9 on 4 minus 9 on 2 plus 1. Common denominator, 9 on 4 minus 18 on 4 plus 4 on 4. So it's negative 9, so negative 5 on 4. Okay, so therefore, gradient is 0 at the point 3 on 2, negative 5 on 4, which makes this the turning point. And this is a really important strategy for finding turning points. We already have other ways to find the turning point of a parabola, completing the square, etc., etc. But up until now, when we've drawn our cubic graphs, our quartic graphs, etc., we just haven't labelled turning points unless we've had a CAS with us. But now we're going to have a way to calculate the turning points of any kind of function that we know how to differentiate. Okay, so the work today is from exercise 17b, practice calculating derivatives, and also some understanding of, making the gradient equal to a value, subbing a number into the gradient, etc., etc.